Let's talk about quotient modules. So let's take a module R, let's take a ring R and a module M over R. R is M is an R module, and N a submodule of M. Okay, now submodule in particular means that it is a subgroup of the additive group, subgroup of M plus, and so we can define the quotient group. So recall, if I have a group and I have a normal subgroup, I can talk about the quotient. In this case, M is an abelian group, so M by N with this addition, I can talk about the quotient group, and this has well, in fact it's an abelian group. And what's the group operation? I take cosets. So firstly, what are elements here? Elements of L look like cosets, x plus n, x varying over m. So this is a space of cosets, set of cosets. And recall, addition of cosets is defined like this, or the group operation is x plus n plus y plus n is just x plus y plus n. Okay, and this is for all x and y coming from M. Now what we claim is that we can do more, because M is a module, which means I know how to do scalar multiplication, and N is a submodule, which means it's closed under the scalar multiplication. So given this additional data, we claim that we can make L can be made into an R module. Okay, so why R? So let's define the action we have in mind. Let's take a ring element R, let's take a coset x plus n, and we will define. So this is the definition, that R acting on x plus n is just R acting on x plus n, meaning the coset of Rx, and this is for all ring elements, for all elements x in n. Okay, so that's the definition of the scalar multiplication. And what we need to do before we even proceed further to show that it is a ring and so on, it's a module and so on, is we must show that this definition is actually well defined. Okay, so why do we need to worry about well defined definedness? Because this coset x plus n, I have chosen one particular representative x from this coset, but of course I could have chosen a different representative. And when I do that, I should ensure that my right hand side, the coset that appears on the right hand side, remains the same. Okay, only then can I claim that this definition makes sense. Okay, it shouldn't depend on the representative that has been chosen. So here's the first thing. Let's check that this definition is well defined. So what should we do? So well definedness means checking the following. Suppose two different representatives, two different elements x and y give rise to the same coset. Okay, then we need to check if the right hand sides that we claimed, so Rx plus n is the same as Ry plus n, and this should be true for no matter which ring element I choose. Okay, so if this happens, then this definition is well defined. Okay, so let's complete the verification here. So what does it mean to say that x plus n equals y plus n? Well, this means simply that x minus y is an element of n. Okay, now n, remember, is a submodule. Okay, so now we use some of the hypotheses. So n is a submodule, means it's closed under scalar multiplication. So what I can do is I can multiply this element x minus y by the element r, so scalar multiply it, and what I will get must again be an element of n. Okay, we're almost there. So now we will just use what's r acting on x minus y, the axioms of modules. The second axiom, I suppose, says that r into x minus y is just the same as r acting on x minus r acting on y. So this says rx minus ry is an n, and of course this just means that the two cosets Rx plus n and Ry plus n are the same. Okay, So that completes the verification that this definition is actually well defined. Okay, now we'll need to check the R module axioms. So, does this make it into an R module? So let me check one of them. All the others are similar. So let's check the module axioms. So axiom 1, for example, so it says that if I take a ring element R and I take the sum of two elements, so here the sum of two cosets, so I have to verify whether this gives me the same answer as R acting on x plus m plus R acting on y plus m. Okay, so I need to check if these two things are the same. So again, let's just compute each side and see what we get. So firstly, x plus m plus y plus m, this is a sum of two cosets. So this by definition, so this here I am just using the definition of addition in the space L, in the abelian group L. The addition is just you add x and y and take that plus m. Now what is R acting on this coset x plus y plus m? Now this is by the definition of scalar multiplication. So this is the definition of addition in my quotient space. So this is now by the definition of scalar multiplication. When I take R and multiply by this, I am supposed to get R acting on x plus y plus m. Okay. Now on the other hand, what I have here, the right hand side, it's R acting on x plus m is just the coset Rx plus m. So I have to here use the scalar multiplication definition first. So this is by the definition of scalar multiplication. R into y plus m is just Ry plus m. And now I use the definition of addition in my quotient space, which is I have to add the two representatives together, Rx plus Ry plus m. Okay, and now observe that these are both equal because of the axiom R times x plus y in my module M is the same as Rx plus Ry plus m. Okay, and so those two are actually equal. Okay, now all the other axioms are similar, so you should just check all the other axioms. Okay, so I will leave that for you to check. So what we have managed to do is show that the quotient group m by n is in fact more than just a group, it's actually an R module. Okay, now in the case of vector spaces, this is it may be a concept that you have encountered in linear algebra. It's usually called the quotient vector space. So let me just make a brief remark about that. This is sort of a standard example, which is if R is actually a field K, M and N are, well, M is an R module, in other words M is a vector space. So suppose M is a K vector space over K, and N is a subspace. So if I give you these two things, then we usually talk about the quotient vector space M by N. Okay, and this is exactly the notion that we have defined here, quotient vector space. Well, how is it defined? It's as an abelian group, it's just the quotient of the abelian group M by the normal subgroup N, and the vector space structure is given by allowing scalars to act in exactly the same way that we just defined. So if I take a element of K, the ground field, then I make K act on the coset x plus n by just making it act on the representative x. Okay, so this definition coincides with a definition which you may or may not be familiar with, the notion of a quotient vector space. Okay, and this is so maybe an exercise. If you have seen this before, if not, we'll do it during one of the problem sessions, is the following: if M is finite dimensional, if M is finite dimensional as a vector space over K, then in fact so is N, any subspace is finite dimensional, of course so is the quotient, and we have the following nice relationship that the dimension of the quotient as a vector space is the dimension of M minus the dimension of N. Okay, so just try proving this using the definitions if you haven't seen the definition of a quotient space before. this involves trying to find a basis, an appropriate basis for the quotient vector space. Okay, anyway, just something to think about regarding quotients. Now here's a slightly less trivial example. Is let's take the ring R to be Kx. So I'm going to talk about a module over this ring Kx, and recall that just means I should give you a vector space together with a linear operator. Okay, so let me take my vector space, K vector space, to be K2, and I should give a linear operator on this space. So let me just give you the linear operator T, which does the following. So the matrix of T is just, so I'll sort of give you the matrix of T, it's 0 1 0 0. In other words, if you want to think in terms of basis vectors, T takes the first basis vector to 0 and the second basis vector to 1. Okay, that's what this 0 1 0 0 means. So E1 is the first basis vector 1 0, E2 is the second basis vector 0 1. Okay, so I given you I've fully specified a vector space and an operator. So I have fully specified the module structure of V as a module over Kx. Okay, so what's the module structure here? So now remember, V is therefore a Kx module via the following definitions. The constants, the constant polynomials act as follows. So if I just give you alpha acting on V, it's just the usual scalar multiplication. So this is if alpha comes from K. This is the constants, and then the special polynomial X acts for all V in V according to the what the operator T is. Okay, the action of X is given by the operator T, and more or less these two are all you need. From this you can figure out how any polynomial acts. Okay, you just have to use higher powers of T. Okay, so we have seen this before. So all I want to do is sort of take this particular example of T and work out what this this module looks like. In particular, this module V has an obvious submodule. So consider the submodule W, which is the span of just the first vector E1 alone. Okay, so this is a subspace. So when I say span, I just mean all scalar multiples with scalars in K. So look at just all multiples C times E1, C coming from K. Okay, so this is a subspace of the vector space V, and I claim that in fact it's actually a submodule for the action of Kx. Okay, so recall what's a submodule. It's just a subspace which is also invariant under the action of T. Okay, so let's check that W is T invariant. So note that W is definitely a subspace. W is a subspace is clear enough, but in fact if I take an element of W and I act T on it, so what's an element of W? Typical element looks like CE1, and if I act T on it, well, by the definition of T, that is just 0. So in fact T of W is actually just going to give me the 0 subspace. So in particular it means that T of W is a subset of W. Okay, that is W is T invariant. Okay, and from our general analysis of what submodules look like, this means that W is actually a Kx submodule. This is a submodule. This is a Kx submodule of the module V. Okay, so we have found a module. So just to recall what T does, so notice this is what T was doing. T of E1 was 0 and T of E2 was, sorry, it's not 1 here, it's E1. T of E2 is E1. Okay, now let's look at what the quotient looks like. So I've gotten a submodule W of V, so I can consider the quotient space V by W. And what does this look like? This is all elements of the form V plus W. Okay, V coming from V. Now let's just calculate the action of Kx. So by our general theorem, or general construction in some sense, the quotient space is also a kx. This should be a module, right? This has a kx module structure. The question is, what is this kx module structure? So a kx module is a vector space together with a linear operator on that vector space. So here the vector space is this, right, the quotient space, whatever that is. But the question is, what's the action of the linear operator that we are talking about? And recall, the linear operator is nothing but how x acts. Okay, so let's figure out how does this special polynomial x act on an element of v by w. So that's my question. So let's answer this question. How does x, the polynomial x, act on v by w? Okay, so let's compute. So let's take x and try to make it act on a coset v plus w. By definition of the action on the quotient space, how does a ring element act on a coset? It just acts on the representative. So this is just x acting on v. So this x acting on v plus w is just x acting on v plus w. Okay. Now recall, x acting on v by definition of the operator t, x acting on v was just the original operator t acting on the vector v. Okay. But now what does v look like? V is some combination of the vectors e1 and e2. So when I act t on it, tv is just well, it's c1 times tv, te1 was 0, plus c2 times te2, and te2 is e1. Okay, now I've used the definition of t here. I've used the fact that when I apply t to e1, t acting on e1 gives me 0. So this is t e1 is 0, and t acting on e2 gives me e1. So t e2 is e1. So I've used those two properties of t here, and what that tells me is that the final answer is just c2 times e1. So when I apply t to v, I just get a multiple of e1. Okay, but notice I am not looking only at tv, I need to look at the coset tv plus w. So observe, my answer here is that x acting on the coset v plus w is tv plus w, but that's just c2 e1 plus w. Okay, but remember, w itself is all multiples of e1, right? So this guy actually belongs to w. This is just an element of w already. In other words, this is therefore the same as the 0 coset. Okay, if I have an element, a representative which comes from the subgroup that you are quotienting by, then of course that plus w, that element plus w is the same as 0 plus w. Okay, in other words, this is just the 0 element of the module. Okay, in other words, x just acts as 0. X kills all the elements of the quotient space. Okay.